Okay, all right. So in chapter 5, we are going to finally define what is a random variable. Okay, but let's go back a little bit and think about the idea of a random process, or a random experiment or a statistical experiment, right? A statistical experiment is just a process with well defined outcomes, right? So it could be coin flip, but it could also be eye color, right? We have known different eye colors, like, among the population, right? And so if I pick a person at random and ask what color is their eyes, I have an expectation, right? It's a well defined. I have a list of colors that their eye could be, right? Or I can ask somebody's gender, right? And there's a list, of what gender they could be, right, as well. And so in the real world, right? Well, let's call this like reality, right? So this is this is reality, right? This is reality, right? I have height, right? I have my coin flips, right? I have my coin flip, right? And I have my gender, right? Gender, a color, right? And things, right? Income, right? And so these are all things that happens, right? These are all these are things that happen in reality, right? Happen, that exist out there, right? And we have a sample space, right? So these, right? There's a sample space, right? There's a sample space, right? That tells me, what are the possible outcomes, okay? But sample space are physical objects, right? And they're hard to work with. Right? So what a random variable does is it takes the elements, right, that's in the sample space, and then it moves them on a number line, right? So there's the real number line, right? Real number line goes from negative infinity to infinity, right? You have 0 here, 1 here, -1, and so on, right? And so now, once it move away, right? So once it so I have coin flips, right? That's heads and tails, and now I can turn them into numbers, and then I can work with them. So, for example, I have a random process here, flipping a coin twice. So let's write out. We've done this a couple times now. Let's write out the sample space. Okay, I have my sample space here. Physical objects. Okay, now I want to convert them into numbers so I can do calculations, because I can't do calculations on coin flips. Right, so I'm gonna define this. Now it is up to the data scientist to define the numbers, right? How you want, right? There's nothing, there's no science here to tell us that a head have to be 0, a tail have to be 1. This is simply a choice. Okay, and so, but I'm going to say, okay, well, the head is 0, so heads will equal 0, tails will equal 1, and then, so I want my random variable x to be the sum, right, of the outcome. Okay, sum of the face, right, the face of the coins. Okay, so then, right, what is then my possible outcome? Well, here we go. Like head, 0 plus 0, so that's 0. Head tail, that will be 1. Tail head, that's also 1. 1 plus 0 is 1. Tail, that would be 2. All right. So then I can do a quick sketch here. I have 0, 1, and 2. These are my 3 possible outcomes. Right? How often do they happen? 0 happens once, 1 happens twice, right? And then 2 happens once. Okay, that is my distribution, right? That is my distribution here. Now, with random variables, right, we want to be able to express what is the possible values. So here, my possible values for this experiment is, again, 0, 1, and 2, right? Because that's where they come from. Now, the 0, 1, and 2 don't happen in the same frequency, right? So I can have a frequency here, right? Then 0 happens once, 1 happens twice, right? And 2 happens only once. Okay, and then I can calculate. Furthermore, I can calculate their probability now. So what's the probability of x? Well, this is 1, right? 1 out of 4, so 1/4. 2 out of 4, so that's 1/2. 1 out of 4, that's 1/4. Okay, so that is going to be the key to random variable. So random variable, we're going to have what are the possible values, and then what's the probability of each of these values occurring. Okay, let's try again here. All right, a random process of rolling 2 die. Okay, define the random variable x as the sum of the outcomes. Okay, all right. And here I think this is a good exercise to help you kind of visualize what happens. All right, I have 2 die, so my sample space, right? My sample space is going to be 1 1, right? 1 2, right? And so on. 1 6, right? 2 1, 2 2, right? And so on and so on. Okay, so I'm not going to write them all out. There's going to be 36, right? There's a 36 different possibilities, right? Possible outcomes. Okay, now the 36 number in the sample, the 36 elements in the sample space. But what about random variable x? Okay, so here, random variable x, right? I have, well here, let's give this a try. So now, right, I can draw a table, okay? And this is my first dice. So 1, 2, 3, 4, 5, 6. Second dice, 1, 2, 3, 4, 5, 6. Okay, and then I'm gonna grab a ruler. Oh, actually, you know what? I don't think I need a ruler here. Okay, and now I'm going to define my x as the sum of the outcome. Again, that's just simply a choice, right? I could easily define x as the difference, right? Subtracting of the outcome, or the product, multiplication of the outcome. But I'm going to say they're the sum of the outcome. So 1 1. So 1 plus 1 give me 2, right? 1 plus 2 give me 3, right? 1 plus 2 give me 3, right? 1 plus 3 give me 4. Okay, and you notice a pattern here, right? 5, 6, 7. 4, 5, 6, 7, 8. 4, 5, 6, 7. 5, 6, 7, 8, 9. 6, 7, 8, 9, 10. 7, 8, 9, 10, 11. 8, 9, 10, 11, and 12. Okay, so what are the possible outcomes here? Well, the possible outcomes are from, right, if x is defined this way, the possible outcome is from 2 to 12. Okay, by the way, this is how the game craps work. Right, anybody play craps at the casino, right? You'll see that like 7 is the most likely number, which is why, right, when you roll a 7, right, the house takes everybody's money, right? Oh, okay, all right. So this makes it right. So now this makes it tangible, right? We're dealing with dices, right? That roll, like we're dealing with rolling 2 die, and then now I have numbers, right? That I can use to calculate. Okay, types of random variable. So in chapter 5, we're going to focus on discrete random variable. Okay, and there will be 2 main types of random variable. There will be a discrete random variable and then a continuous random variable. Okay, so first of all, what is a discrete random variable? Okay, so a discrete random variable, right, it's a random variable that has a countable number of possible outcomes. Okay, now what is countable? So the idea of countable is a mathematical concept. Okay, all right. So for example, right, I have the natural number set. Okay, so this is a natural number set. Natural number starts at 1, 2, 3, and so on. It goes to infinity, but it just keeps going, right? It is a natural numbers 1, 2, 3, 4, 5. Now 1, 2, 3, 4, 5. This is countable because I can move forward. I can move forward. I can go from, right, if I put this on the number line, 1, 2, 3, 4, and so on, I can go 1, 2, 2 to 3, 3 to 4, and then I can keep counting. So this is discrete because it is countable. Now let's take the real number, right? Real number line, right? Or the real number 1, 1.1, 1.111, 1.11111, and so on, right? And now this also goes to infinity. However, I can't count it, right? I can visualize it better if I draw it on the number line, right? So let me start at 1. I want to count to 2, okay? Right? Is it possible to count every number that's between 1 and 2? Right? No, because I can count 1.01 and then 1.1.001, right? And so on, right? Okay, that's not how you count, right? This is bigger. So we count. Anyway, get my point. There's infinite, right? Between here, there's infinite number, right? There's infinite number of numbers, right? Between any 2 points. And so I can't move forward. I will never finish counting here. So this is what we mean by not countable, right? This is not countable. So now we're going to use this rule, right? Although a little bit loose. We're going to use this rule to define what is a discrete random variable and what is a continuous random variable, right? So if we're going to say it's countable, meaning that we're not allowing any value to be between two numbers, then it is countable. However, if we're going to allow some decimals, right, or fractions of, right, in between, then it's not going to be countable. So in the previous example, right, the random variable x has 11 countable outcomes, right, all the way from 2, 3, 4, right, all the way to 12. So there is possible when you roll 2 die, and if you define x as the sum of the outcomes, then there are a total of 11 different outcomes possible. Okay, and each of them obviously will have a different possibility, right? So continuous random variable, like we said, right, it is not countable. Okay, so so things like height, income, and age, right? So if I have height, right, now you might say, well, aren't we just going down to inches, right? But it is possible, right, that, so for example, I can have 5 foot 3 inches, right? But we are allowing, as we collect the data, we are allowing for the fact that there is 5 foot 3, 3.5 inches, right? For example, right? And now in data collection, generally we do not go deeper than that. But the fact that we're sort of allowing, right, the values that we collect to take place, right, to have multiple values, right, or we're essentially saying, right, it can take on, in theory, any value between 5 foot and 6 feet, right, 6 foot, for example, right. Even though, yes, we're not going to get that precise in the measurement, we're still going to consider this continuous. Okay, just like income, right? Income could be, income, right, as a random variable, right, could be between $0 and all the way to, I don't know, $1 billion, right? Right. Oh, shouldn't have said a billion. Okay, now $1 billion. Now, it could take on, right? It could take on any number in between, right? In between any two numbers as well, right? So I can pick any interval. I can pick between $5 and $10, or maybe $5 and $6, and then I can break it down into deeper as well. Right? Now you might say, well, wait a minute, we don't go beyond cent, right? But this is what I mean by, we're going to treat this kind of loosely, right? The main thing is, continuous random variable, we can do more math to it, right? We can add, we can subtract, we can divide, and we can multiply, right? Right. Whereas discrete random variable, right? Whereas a discrete random variable, right? It's going to be much more. It's going to be much more limited. Okay. All right. Anyway, well, as we do more examples, I think it'll become clear. It'll become clear. So, like I said, we're gonna apply this rule kind of loose, like a little bit loosely, because we're not gonna be that rigorous. The idea of countable, right? Or count or not countable, right? Okay. So, for example, right? Let's look at these examples, right? Take a little practice, right? And then pause video if you want, and decide that go for each one. Decide whether or not that they are continuous, or they are discrete or continuous. Okay. All right. So, all right. Total point score, discrete, right? Because we're not allowing, let's say, 2.5 points, right? We're just that is not a possibility. Daily price of a stock, continuous, right? We go down to the decimal, and if we divide, right? If we do some numerical process, right? If we divide, and it's supposed that we get more than 2 decimal places, well, we could still round, right? That is that is a possibility. Okay, so because we have that flexibility, we're going to consider that continuous. Interest rate, same idea. Interest rates can go down to multiple decimal places, right? We're allowing, right? So any 2 points, right? Any 2 values that we pick, we're going to allow, right, some number to be in between that. Right? So that's continuous. Number of time a backup of computer network is performed. Right? You can't have half a backup. Right? At least, I don't think you can have half a backup. If that's the case, then that was going to be discrete, right? You have a set number. It's always going to be a whole number. Okay. This one's a little bit trickier, right? Amount of sugar. So it really depends on how the amount of sugar is measured. If it's measured in value, like in dollar terms, then it is continuous. But let's just say that if this is measured in bags, right? Bags, then it is discrete. All right. Now, what is a probability distribution? Okay, so it's a model that describes a specific kind of random process. Okay, because we start out with a random process, let's say like roll of a dice, right? And so the random process will have 1, 2, 3, 4, 5, 6, right? This is all the 6 possible outcomes, okay? And then I'm going to define x, right, as the value of the roll of the dice. Right? So I take something that happens in the physical world, and then I put numbers. I define a random variable based on it. Okay. So there are two things that's most important about a random variable. Then, right? One, xi. Right? One is the possible values. 1, 2, 3, 4, 5, 6. Now that's how I define it. Right. So for example, right, if let me do a different example. For whatever reason, right, I want to define, right, the roll of it instead, right, define x as the square of the value. Okay, then in that case, xi, right, it will be 1, 4, 9, 16, 25, 36, right? So that will be the same random process, right? The same random process. Depending on how I want to define the random variable, I could have completely different, right, values. Now, what's the probability? So the probability, right, of that, well, each of them is, right, in order for me to see a 1 here, I have to roll a 1. So, right, so then this is 1, 1, 6, right? And this is also 1, 6. And actually all the way down, that'll get 1, 6 all the way down. Now what about here? Just because I define the x as some, square of the value, it doesn't matter, because in order for me to get a 1, I still have to roll a 1. So that is a 1, 6 probability. How do I get a 4? I have to roll a 2. I have to roll a 2 to get a 4. So that is still 1, 6. 9, how do I get a 9? I don't have to roll 3 to get a 1, 6. And so on. Right? So 1, 6, 1, 6, all the way down. Okay? A probability distribution is something that describes a random process. It is a description of a real thing. Okay? So we're going to have multiple ways of describing it. Okay? So this is the table form, or tabular form, right? We have what are the possible values, and then what's the probability of each of them. So this is one way to describe what is a probability distribution. Now this is the table form, but I can also do a graphical form, right? So how would I describe this probability distribution in a graph? So let me do it here. I have 1, 2, 3, 4, 5, 6. And I can do this in a histogram, right? Or something that looks like a histogram. Now, this is, and then we'll talk more about this, but this is I'm going to get a flat line here. Right? I'm going to get a uniform distribution, okay? Because all the height is the same, 1, 6, right? 2, 3, 4, 5, 6, right? So it's a flat line, that gives me a rectangle. So this is a graphical form, or graph. And both of these ways are describing the probability distribution. Okay, so this chapter, like I said, we're going to focus on discrete probability distribution. There are a couple of rules in order to be a proper probability distribution. These first two, we've seen those already, right? The sum of every possible outcome, the probability, that is, of all possible outcome, must add up to 1, right? Because otherwise, something else must be happening. So so it has to add up to 1. We account for everything. What does that look like? Well, here are the, let's say that here are the possible outcomes, right? x1, x2, x3, all the way to xn, probability of xi, right? And this would be 0.32, 0.05, and so on, right? They have to add up, right? If I add them all up, it has to equal 1, right? These are all the possible values. Second, probability still can't be negative, and it can't be greater than 1. Okay, so if it's that, then it is invalid. And we're going to add one more. The probabilities are additive. Okay, now this is the probability of x equals xi or x equals xj, right, equals then the sum of those two. Okay, all right. Now, what does that mean? That means the union, that means A. So here, I'll give you an example here. If this is my distribution, right, I have A and B as my outcome, right? And here, here's the probability of A happening. Here's the probability of B happening, right? Okay, that and the probability of xi. So that means that the probability of A or B, right, A union B, right, equals probability A plus probability B. That also means, remember from last chapter, that the probability of A and B equals 0. There is no intersect between them, right? That means any process, right, cannot be both A and B at the same time. So every observation or every outcome, every number here has to be unique, right? Or what, not unique, but yeah, you can't. It has to be one of these and not both. Okay. All right, and it's you think of roll of a dice, right? It's either a number from 1 through 4. I'm sorry, 1 through 6. It can't be 1 and 6, right? There's just no that just would never happen. Okay, so that's what this last part means. Okay, all right. So, for example, right? Let's check. Well, let's see. Is this a probability distribution, right, for random variable x? Well, first let's check. Okay, less than greater than 0, less than 1 checks out. Let's add it together, equals 1. That also checks out. Okay, now I want the probability of 3, right? 3 or 6. Okay, how do I get that? Well, then I just add up 0.25 plus 0.5. Okay, then that means 0.75. Right? What this means is if I select one of the outcomes or at random, right? What's the probability that I get a 3 or a 6? Well, then it's 0.75. Okay, that's the probability. Okay. All right. Now we already talked about this one, right? But so there are some discrete probabilities that is very convenient. So we give them names. Now, of course, in theory, there's infinite amount or infinite types of discrete probability or any probability, but some are very useful, so we give them names. So discrete, right? Where the discrete uniform probability, it just means that every outcome, right, every number has the equally likely outcome. Okay, so a discrete probability table looks like this. Right? Right, so I have x. I have x here, right? Maybe I have 2, 4, 6, 8, right? 2, 4, 6, 8, 10, right? So that's I have 5 numbers here. Then if we say that this is a uniform distribution, then that means my my probability, right? P of x. By the way, P of x and f of x, we're going to use them interchangeably. Okay, my P of x is 1 over n. So in this case here, my n, that means number of outcomes, number of possible outcomes equals 5. Right? So this will be 1/5, 1/5, 1/5, 1/5, 1/5. Right? Each of these numbers have the equal opportunity or equal probability of outcome, or sorry, equally likelihood. Right? And that's what uniform just means. So if you're told that a distribution have a uniform distribution, then you know that every outcome is equally likely. So that's all it means. Okay, very simple. We're seeing a dice roll. So a dice roll, it is an example, right? All right, of uniform distribution, right? So we can write f of x here, right? Then it's 1/6 all the way down, 1/6. Okay. All right. And uniform distribution, I'll just say one more. Uniform distribution will have a rectangular shape. Okay, so here, will be your f of x, right? F of x, that would be the shape, right? And then this will be the starting point, right? And then the ending point, right? Of that distribution. All right, now a probability distribution is just a way of describing something, right, that exists. Okay, so there are many things that we can calculate regarding a probability distribution. Okay, now the two most important things that we can calculate about regarding a probability distribution is expected value and variance. All right, now. Right. So expected value is basically the mean, right? The average of the probability, the average of the distribution. Okay. All right. Now, so the average of the distribution. Now, here the notation here is going to look a little funky, but this e, right, okay, I'm going to write it out here. So the mu, the average of the probability distribution, right? And oh, by the way, when I say probability distribution, I also mean meant a random variable x. Okay, so probability distribution or the distribution of x, right, or x the random variable, right? That all mean the same thing. Okay, so the random variable x, right? It's the mean of x, right, is calculated like so. We call it the expected value, right? It's expected value of x. So here's the expected value. Okay, now what does expected value look like? Well, it is the sum of x times probability of x. Okay, so remember, x just means the possible outcomes. Right? And so every possible outcome, right, will have a probability attached to it. So you multiply them together and then you add them together, right? So really the expected value is like a weighted, right? It's like a weighted average, right? Oh, if I want to find I want to find the expected value of x, right? Then, I can look at this table. So I can look at this table here, okay? And here are my x value. Here's my possible x values, right? So my my x variable is the number of sales per day, okay? So I'm calculating, okay? So first of all, is this discrete? Yes, right? Because, well, I can count them out, right? And there's a set number of outcomes, right? Well, it could be infinite. I mean, let me say that first. It could just be infinite, but I can count them, right? I can keep counting and I can move forward, right? So this is a discrete random variable, and for each of these, I have a distribution. Right? Oh, sorry, I have a probability. Right? There is a 0.3 chance, there is a 0.3 probability of getting 2 sales per day. Right? There are 0.2 probability of getting 4 sales a day. Okay, and so to calculate expected value, I multiply across. So this is x times probability of x. Okay, so multiply across, and I will get these values. Okay, and then to get the expected value, you just add them up, all right? So expected value is 2.1. All right, what that means is the average number of sales per day, right, is 2.1. We can also say, right, if I randomly pick a day, what is the expected number of sales? Then we will also say 2.1. Okay. All right, expected value, we can kind of interpret it as what we expect to see. Okay. Now, another example, right? What is the expected value of a coin flip if h is 0 and t equals 1? Okay, so of a coin flip, so define my random variable, my xi, right? My random variable x, right, is going to be 0 and 1. Now, what is the probability of each of these? Well, head is 0, so that's 1/2, and tail is 0, that's also 1/2. Okay, let me calculate the expected value then. Expected value of x equals 0 x times 1/2 plus 1 times 1/2. Okay, this is obviously going to be 0, 1 and 1/2, so it will be 1/2. So that means if I flip a coin and I define head as 0 and tail as 1, then then if I keep flipping, then I'm expecting my value, right? My average value will be 1/2. Okay, all right. Next, variance. Okay, so variance. This looks even more complicated. But variance is how we defined it before. It's basically just sigma square, right? And we're gonna have sigma square for the random variable x, right? And for the probability distribution. Okay. Again, I'm repeating twice. I'm repeating myself because when we say the variance of random variable x is the same as saying the variance of the probability distribution for x. Right. Okay, so sigma square, we also write it like this, variance of x, right? So this is by the way, this notation is very convenient because sometimes we will be talking about different random variables. So this is very useful to say explicitly, this is the variance of x, right? X variable. Okay, and what is this equal to? Right, it's the summation, right, of x minus mu squared times probability of x. Okay, so it still looks like a weighted average, right? I'm taking x minus the expected value or the average, squaring it, okay, and multiply by how likely each of those will occur. So it looks very similar to the variance, the traditional variance formula that we already know. All right, here, what is the variance of a coin flip? Well, let's try to, okay, let's go ahead and use the column method here. Calculate variance. I have 0, 1, right? I have the probability of xi, right? Which is 1/2 and 1/2, okay? And then, furthermore, so now I want x minus mu. So xi minus mu, right? Right? I already calculated the expected value here earlier. By the way, this is mu, right? This equals mu because expected value is mu, okay? It seems confusing now because you're not used to the notation, and you're not used to the notation, and so you just want to be comfortable, right? Of knowing that when you see expected value of x, you know that we're talking about mu, right? You see sigma square, we're talking about variance. Okay. By the way, the reason why we're using so many of these things is these are the population parameters, right? The Greek letters. These are operators. Expected value is an operator, variance is an operator, right? And so that's how we calculate. Now at this level, we're not going to make a big deal about distinguishing between the two, right? But you want to use these are the notations that you will see in your textbook, right? So xi minus mu. So basically this is 0 minus, right? 0 minus 1/2. So I get negative 1/2. Okay, and here 1 minus 1/2. So I get 1/2. Okay, now you notice if I add them up, I'll get 0. That's no good, right? So now I want to square it. So xi minus mu square. I square that, I get 1/4. 1/2 square is 1/4. Okay, now, well, before I add them, I have to multiply by this probability. So xi minus mu square times probability of xi. Okay, so that's 1/4 times the probability of its likelihood. So 1/4 times 1/2, that's going to give me 1/8. 1/4 times 1/2, that will also give me 1/8. Now I add them up. So now I add up these two. 2/8, right? Which gives me 1/4, right? And that is my variance, right? So my variance is 1/4. So in a coin flip, if head is 0, tail is 1, then my expected value is 1/2 and my variance is 1/4. Okay, let's do one more example here. I have a table, right? And I have a random variable y. Okay, don't get too hung up on x, y, or z, right? We are free to choose whatever letter, whatever letter we like, right? So here is a random variable y, right? And they are 1, 2, 3, 4 possible values, okay? By the way, let me just emphasize again, random variable y will always be in terms of a number, okay, right? So there are possible values, so 2, 4, 7, 8, and this is the probability, right, of each of those values. Okay, so I want to compute the expected value of y. Anyway, feel free to pause and check your answer. Check your answer when you're ready. Okay, so I'm going to take advantage of the fact that I have a table ready over here. So I'm just going to add a column, and this column will be y times the probability of y, and then so I just simply multiply across, and then I can just add down this way. All right, so I'll just do that in my calculator here. 0.4 plus 1.2 plus 2.8, and then plus 0.8. Okay. 5.2, right? That's the expected value of y. Okay, now let's go ahead and use, so for the variance of y, you probably want to use, right, probably want to use the table as well. So I will recommend creating a table, so y minus mu, okay? What is mu? I got mu right here. This is mu, right? So y minus mu here, and then y minus mu squared, okay? And then finally, y minus mu, right, squared times, right, times y, f of y, okay? All right, so take a moment, go ahead and make those three columns. Okay, check your column. I think I got this right, or I think I'm pretty confident in my calculator skills. But here, y minus mu, so every number here, minus 5.5, you get that. Now, this column, you just square every number here. So this is 3.2 square gives you 10.24. 2.8 square gives you 7.84. Okay, finally, take this column, multiply by this column, right? 10.24 times 0.20, right? You get that. Right? And here, I want you to get try to develop the intuition when you look at these formulas, right? Think about why this makes sense, right? This is this is the deviation, right, of y from the mean, right? So this is the deviation of 2 from 5.2, okay? And then you're multiplying by the probability, right? Just to calculate or put a weight that how often this happens, right? So basically, you're saying, okay, 0.2, or we can say 20% of the time, 2, right, is it is 5.2, so it is 3.2 away, right, from the mean. Okay, and then we just add up. So we add up together, right? So we can add all this together and be right. Once you add down, we can get variance, right? Variance of y. Oh, by the way, var equals v of y, right? They all mean the same thing, shorthand, right? They mean the same thing. If you add all that together, right, you will get 4.56. Okay. Now, how do I get standard deviation? How do I get sigma? Well, remember, variance of y is just sigma squared. So if I want sigma, then I'll just take the square root of sigma squared. Oh, therefore, the square root of 4.56. Okay, put that in the calculator, and you should get 2.14. Okay. All right, so that is part 1 of handout 5.1.